All right, let's move on to 5.2. In 5.2, we're going to talk about verifying trig identities. And this is going to be useful information for us as we move through the rest of the chapter. Because we're going to want to prove a bunch of the identities on that list that I gave you in the previous section, right? So this list of trig identities, we want to be able to prove all of these things. So we'll talk a little bit about some common tricks and techniques for verifying trig identities. So here are some suggestions for you. If you haven't done so already, you really need to commit to memory the fundamental identities that we talked about in the previous section. Okay, but also familiarize yourself with some of the equivalent forms. So, for example, one of the things that we saw at the end of the last section was that we have this Pythagorean identity sine squared plus cosine squared equals 1. So you should have that memorized, but you should also realize that anytime you see something like 1 minus sine squared, you should kind of automatically think in your mind, oh, I can replace that with a cosine squared, right? So don't just have like these identities memorized, but also have their equivalent forms, their equivalent formats kind of in mind. When it comes to verifying an identity, if one side is clearly more complicated than the other, then it's usually easier to start with that side and try to transform it to the simpler side. If both sides are complicated, though, then you can kind of work independently on each side and try to meet in the middle somewhere. If you get stuck, a good trick is to change everything into sines and cosines. I do that a lot. That's sort of my go-to thing, is to just change everything into sines and cosines if I find that I get stuck. Sometimes it makes things messier, but like I said, if you're stuck, then that's a good thing to try. And then don't forget your algebra, of course, right? So as far as factoring is concerned, right, like sine x plus 1 quantity squared, right, is just sine squared x plus 2 sine x plus 1. I was missing an x there. So you can always swap these things out for one another as occasion may require, right? If you have a couple of fractions, right, you can add those by getting common denominators. You can multiply things by their conjugates. So if you had something like 2 over 1 plus cosine x, but on the other side you notice that you had like a 1 plus sine x over 3 or something, right? Then that might tell you, oh, maybe if I multiply by the conjugate 1 minus cosine x, then I can sort of change this thing so that the sum is occurring in the numerator rather than in the denominator, right? So these are common tricks that we might appeal to as we're trying to verify some identities. So let's get to it. I have 5 examples that I want to show you, and I haven't worked these out yet, so wish me luck. Okay, so let's verify some identities. Let's do tangent alpha over secant alpha equals sine alpha. So I should say, I guess, before we get started, that we're not trying to solve this equation. Okay, so we're not trying to find the values of alpha that makes this statement true. If this is an identity, then this is true for every value of alpha where all of the functions are defined. Okay, so we're not trying to solve for alpha. We're trying to verify the identity. So we're trying to fix up one side of this equation so that it looks like the other side of the equation. Okay. First of all, I noticed that the left-hand side is more complicated than the right-hand side. Not too much more complicated, but slightly more. The right-hand side of the equation is just a sine function. So that kind of tells me if I rewrite these things in terms of sines and cosines, I might be able to get a sine out of this. So let's see. So I'm going to start with the tangent alpha over secant alpha. And let's rewrite it in terms of sines and cosines. So tangent is sine over cosine. and secant is 1 over cosine. So maybe I'll write it like this just to make it less confusing, right? So tangent alpha over secant alpha is the same as tangent alpha times 1 over secant alpha. Okay, but 1 over secant is just cosine, right? So this is sine alpha over cosine alpha times cosine alpha. And sure enough, the cosine alphas cancel, and we're left with sine alpha, just like we were hoping for. Okay, so this is how we verify trig identities. We work on one side until we get it to look like the other side. Or in the case that you have a trig identity with 2 complicated sides, then you might work on both sides and try to meet in the middle somewhere, like we said, but this is the idea. Okay, let's do another one. Let's do cosecant theta equals tangent theta over secant theta minus cosine theta. Okay, so I'll let you pause the video and see if you can work this one out. Alright, so this time I think the right hand side is the more complicated of the 2 sides. So I'm going to start there and see if I can manipulate this thing to get it to look like cosecant theta. So one thing that occurs to me immediately when I look at this is that I know that secant theta is just 1 over cosine. And I know that tangent theta is sine over cosine, so I guess I'm sort of thinking of going to sines and cosines again. Let's see where that gets us. Okay, so the next thing I would think to do would be to clear all of these complex fractions by multiplying by cosine theta in the numerator and denominator. And I'm not sure if that'll get us anything beneficial. Maybe it will. Let's see. So we're going to have sine theta in the numerator. In the denominator we'll have a 1 minus cosine squared theta. There it is, right? So remember, 1 minus cosine squared, this is Pythagorean identity, right? Sine squared plus cosine squared is 1, and so therefore 1 minus cosine squared is sine squared. So this is going to be sine theta over sine squared theta. Well, so one of the sines will cancel. So this is just 1 over sine theta. And then you have the reciprocal identity, right? 1 over sine theta is cosecant theta. And that's exactly where we were trying to land, right? So, so that does it for part B. It should go without saying, right? There's more than one way to do these problems. So if you did this differently, that's fine. Like one of the things I was thinking of when I first looked at it is I was thinking, well, secant is 1 over cosine, and so maybe I can get a common denominator and add these things together or something. I don't know. Something like that may have worked out just as well as what we did together. So let's do another one. So let's do sine beta over 1 plus cosine beta equals 1 minus cosine beta over sine beta. Oh, that's interesting. That's an interesting one. They're very similar looking. But it's almost like when you flip it over, you've got to change the sign from addition to subtraction. Well, not almost. That's exactly what's going on. It's kind of interesting, though. So this one, well, yeah, go ahead and give the video a pause and see if you can work it out. Okay, so on this one, neither side is more simplified than the other. I mean, I think they're equally challenging, I suppose. So I'm just going to start on the left-hand side and see what I can do with this. And from experience, what this looks like to me is that I'm going to have to multiply by the conjugate. And the reason I'm thinking that is because the sum on the left-hand side is taking place in the denominator, whereas on the right-hand side it's taking place in the numerator. And so if I multiply by the conjugate, that's going to clear the sum in the denominator, and it's going to give me a sum in the numerator, which is exactly where I want to kind of end up. So I'm thinking multiply by the conjugate is probably the way to go here. So let's do 1 minus cosine beta over 1 minus cosine beta. Not sure how much of this I really want to multiply together. I might just leave it factored like this, in the hopes that maybe this sine beta will cancel. Let's see. So here if I FOIL, I've got 1, the negative cosine and positive cosine will cancel, and then I'll have a negative cosine squared beta. Oh yeah, there it is, right? This is going to work out nicely. So we'll have sine beta times 1 minus cosine beta. 1 minus cosine squared is sine squared. I think we just saw that trick in the previous problem. And then one of these sines will cancel one of those, and you'll end up with 1 minus cosine beta over sine beta, which is exactly where we want it to end up. Okay, so there's that one. Two more. Okay, this one looks like kind of a monster. Let's see. So we've got secant theta minus tangent theta squared plus 1 over secant theta cosecant theta minus tangent theta cosecant theta. Okay. Equals 2 tangent theta. So supposedly all that stuff on the left hand side is just equivalent to 2 times tangent theta, which is interesting. Okay, go ahead and give the video a pause and see if you can work that one out. Okay, so here we go. I'm definitely going to start on the left hand side. Looking at the, let me rewrite it real quick. So secant theta minus tangent theta squared plus 1 over secant theta cosecant theta minus tangent theta cosecant theta. Okay, so looking at the secant theta minus tangent theta squared, that's really close to a Pythagorean identity. So the way that it's listed on your formula sheet is tangent squared theta plus 1 equals secant squared theta. But if you rearrange those terms a little bit, then what you get is secant squared minus tangent squared equals 1. Unfortunately, that's not what we have here, and if you're thinking that you can just distribute this 2, think again. So exponents don't distribute across addition and subtraction like that, right? So you'd actually have to FOIL this thing out. So unfortunately, we can't just replace this with 1. But we might end up FOILing it out. Actually, that might be what we end up having to do. Not exactly sure what to do there. In the denominator, we can definitely factor out a cosecant theta. Again, I'm not sure if that's particularly useful. If we were to factor out the cosecant theta, then we'd have a secant minus a tangent. Secant is 1 over cosine, tangent is sine over cosine, so it would just be 1 minus sine over cosine. We could clear everything by multiplying by a cosine theta. Alright, so I think I just need to write some stuff down to try something out. And here's what I think I'm going to try. I think I'm going to go ahead and FOIL out the secant theta minus tangent theta squared. And then I'll factor out the cosecant theta from the denominator. So I'm going to try both of those things. So if I FOIL this, I've got secant squared theta, and then I'll have minus 2 secant theta tangent theta. I'm almost certain that's where the 2 tangent theta is going to come from. Maybe I shouldn't be so sure, but and then plus a tangent squared theta, and then plus 1. And then here I'm going to go ahead and factor out that cosecant theta. Okay. Can we simplify any of this with some Pythagorean stuff? So yeah, tangent squared theta plus 1 is just secant squared theta. So I can replace this with a secant squared. And then I've got a secant squared, and a secant squared will give me 2 secant squared, which is nice. So let's do that. What about that denominator? I'm not sure what to do with that yet. I know I can factor out a 2 secant theta. That might do something nice with this cosecant out there. Yeah, okay. So let's factor out that 2 secant theta. And I'll be left with a secant theta minus a tangent theta. There it is, right? Or cosecant theta times secant theta minus tangent theta. Okay. And then those are gone, right? So we've got 2 secant theta over cosecant theta. Now where am I trying to land? I'm trying to land at 2 tangent theta. So I think if I change these probably to sines and cosines, I'll probably get there. So secant, so this is going to be 2 times secant theta times 1 over cosecant theta. And let's change all these to sines and cosines. So we're going to have 2 times secant is 1 over cosine. Cosecant is 1 over sine. So 1 over cosecant is sine. There it is, right? So this is 2 sine theta over cosine theta. That's just 2 tangent theta. Alright, so that, I mean, that wasn't actually so bad. I think it was mainly just algebra, factoring stuff. Really the only trig identity that you used is the tangent squared plus 1 equals secant squared. I'm saying you, but it was me, right? I'm the one who used it. Anyway, that was the only trig identity I used. I think everything else was just algebra on this one. Okay, so that's that. Again, more than one way to skin a cat though, right? Like, I mean, if you thought of a different way to do this and you landed there at 2 tangent theta, I mean, I can't say for certain that it was correct, but there's a good chance that it's a correct solution. Goodness gracious, one more. Okay. Let's do sine to the 4th alpha minus cosine to the 4th alpha over sine squared alpha minus cosine squared alpha equals 1. Okay. So here I think I'm going to be doing some more algebra probably. I mean, sine squared plus cosine squared is 1, but this is sine squared minus cosine squared, so we don't really have an identity for that yet. We'll have something that'll be nice for that a little bit later on. But I can definitely factor those because this is a difference of squares, right? And so is the numerator. So let's factor. I'm just going to go ahead and factor this. So sine to the fourth alpha minus cosine to the fourth alpha. This is going to be sine squared alpha plus cosine squared alpha. Ooh, that's nice. Times sine squared alpha minus cosine squared alpha. Right? Difference of squares. In the denominator, I think I'm just going to leave this as sine squared alpha. This one was super easy, as it turned out. Because now this will cancel there. So we'll just be left with sine squared alpha plus cosine squared alpha. I feel robbed. I feel robbed of an opportunity to do some nice fun trig. But that's just one. Okay? So that's just a 3-step problem. So that's not bad at all. Anyway, so as you can see, like most of this stuff is algebra. Most of this stuff is just knowing algebra really well. Occasionally, right, you'll have some trig stuff that you need to take care of. So like here we use the Pythagorean identity. Here we use the Pythagorean identity, right? But otherwise, like the trig itself is not terribly complicated. It's mostly just algebra. So that's all I have to say about that. We'll be verifying some more trig functions or more trig identities throughout this chapter as we start to talk about some of these more complicated identities. All right.